Okay. So I think we can get started. Yeah, so it's my pleasure to introduce Professor Alejandro Manjavacas, if I pronounce it correctly. Yeah, he got his PhD from Spain in 2013, and after that he did his postdoc in Rice University with Professor Northland. And his research focused on theoretical nanophotonics. Right now, he's an assistant professor in Department of Physics and Astronomy at the University of New Mexico since 2015. And he has received several awards, including the Foundation Awards to the best young theoretical physics in Spain. And his focus, the focus of his research right now is to understand the fundamentals of light-matter interaction at the nanoscale. And he has co-authored tens of papers and received thousands of citations. So I'm quite glad to have Alejandro here today. So let's see what he brings today.
Okay. Well, thank you very much for the invitation. It's really great to be here and see all the work that you do. So today I'm going to be talking about some work that we've been doing in my group at the University of New Mexico. And then kind of the common theme of all the different projects I want to show you is just this idea of collective effects that arise when you have an ensemble of nanostructures that have some periodicity, some ordering. And then in particular, the three projects I want to talk about are kind of summarized here with these kind of artistic figures. And they are essentially about the idea of seeing or trying to understand how, when you have an array of particles and then you start playing with the unit cell and putting more particles on the unit cell and moving them around, how you can kind of predict the response in a way that is kind of intuitively and then allows you to engineer that response. So I will describe some results we have in a kind of a very simple model that we call kind of a hybridization model that allows you to predict the response of arrays with particles with more than one particle in the unit cell. Now, connected to that, the second part of my talk will be devoted to talk a little bit about which is the limits or which are the limits that a system that has periodicity, and again we are going to be focusing on arrays of nanostructures, which are the limits to the near field that those structures can produce. Now we know that if you have a nanostructure, especially if it can support plasmonic modes, when you shine light, it's going to produce very strong near fields. But then what are the limits you can get when you order them? And if you can really reach very strong fields, and how, under which circumstances you get those fields. And the final part of my talk is going to be kind of trying to connect those two topics to more realistic implementations, because we know that even though for theory, we love to work with periodic systems, which we consider perfectly infinite, and then we can just say, okay, we have just periodic boundary conditions. Of course, when you go to the lab and you try to fabricate any, you cannot make an infinite system. You can also make, you can only make certain size and certain number of periods. And then we want to understand how truncating that periodicity, right, having a finite structure actually influences the predictions that we have been making in these other two parts. So, but before getting into the details, I would like to review a little bit the background of essentially the basic concepts of the different topics I'm going to be talking. So, as you will see, one thing that will appear all the time is this idea of surface plasmons. We are going to be dealing mostly with metallic nanostructures, and metallic nanostructures are interesting for us because they support plasmons. And plasmons are essentially collective excitations of the metal, of the electrons in the metal, not the conduction electrons that you have in those metallic nanostructures, coupled to an external electromagnetic field. This is a very simple way of understanding these structures or these excitations. So if mind you have a metallic sphere of, let's say, hundreds of nanometers, and then you can think in a very, very simple way as, on this structure as if it were composed of two parts, like a positive charge distribution, which accounts for all the atoms and all the electrons except one electron per each atom. That's kind of the usual thing for noble metals. And of course, then you have the free electron cloud, no? Which For example, again, for a noble metal like silver, you're going to have one of these free electrons. Those are the electrons that are on the S band. They can move freely across the metal. And then when you think on the system to be composed of these two parts, and then you shine light on it, of course, you're going to get a charge displacement. You're going to move the electrons with respect to their equilibrium positions. And therefore, there's going to be a restoring force that will pull them back to the initial configuration. And that's, of course, the same as the typical harmonic oscillator, a spring with a mass. And then that's going to give you a system resonance. And that system resonance, that's the resonance we are focusing. This is the localized surface plasmon that each of these nanoparticles can sustain. Plasmons are not new. Actually, they were used by Romans, and this is a very beautiful example of that. This is a cup that is called the Licarius cup, which is very common to be shown in this type of talks about plasmonics, because it has this beautiful property that depending on how you set the illumination, this is from illuminating the cup from outside, this is the same cup but illuminating with light in the interior, you see there is a beautiful change of color of the glass. And this change of color is actually due to the fact that the glass contains gold nanoparticles. And of course the difference on the colors is just associated with the optical properties that those gold nanoparticles produce. And those properties are, of course, determined by the localized surface plasmon they sustain. So indeed what happens is when you illuminate the system from outside, you are seeing the light that is being scattered by those gold nanoparticles. So you shine light, you excite the plasmons, which for gold nanoparticles of this size are typically in the kind of around 500 nanometers, so essentially green light, and then you see the light that is coming from that scattering. However, if you illuminate from the interior and you observe from outside, what you see is the light that has not been absorbed, right? And then, of course, you see the light that has not excited plasmon. So if you take away the green part of the spectrum, you are left with mostly red light. And of course, you also get rid of the blue, because even though you don't have plasmons excited on the blue, you have always interband transitions in the gold, which come from essentially bringing electrons from the D to the S band, and those produce absorption. So for us, plasmons are interesting because when you shine light on a nanoparticle and you excite one of these excitations, then what happens, if you look at the near field, for example, here is a gold nanoparticle of 100 nanometers, illuminated at 510, which is exactly the resonance of the plasmon that it supports. You can see that if you calculate the near field around the particle on resonance, you get a very strong field, and that is very concentrated in a very, very tiny volume. Okay, if you think on confining electromagnetic fields using lenses, you are always limited by the diffraction limit. However, here you see we can confine the electromagnetic field on a region around the particle that is of the order of 10, 20 nanometers. And of course, with the strong confinement, associated with that comes a very strong field enhancement. Here you are having a factor of 10 on the field around the particle, a factor of 10 compared with the plane wave that you are using to illuminate the system. You can do much better. Of course, this is kind of the simplest geometry. You can work a little bit harder and trying to design better geometry, like for example a dimer, where you see you now confine the field in even a tinier volume, and because of that you get a much stronger field. So this ability of confining the electromagnetic field well below the diffraction limit, with the enhancement in the field intensity that comes associated with it, are probably the two properties that are very useful from plasmons, and that are used for a variety of applications, ranging from, for example, ultrasensitive biosensing. You can think that if you want to detect some molecule or some analyte, and you want to use light for doing that, then at the end what you always do is to shine light and try to see any signature of the presence of that analyte. But then usually molecules are very tiny, they have a small cross section, so then you need to have enough of them in order to detect a change. If you instead put those molecules you want to detect in a hot spot created by one of these plasmons, and then you get a field enhancement that could be of the order of 100 or even larger, then you can reduce the amount of molecules you need to have enough signal by that factor, right? Because you are enhancing the interaction. You can also use plasmon for photothermal cancer therapy. This is an application which essentially relies on using the fact that those nanoparticles, when you shine light at the plasmon resonance, they absorb a lot of light, and therefore they increase their temperature. And the idea is that if you can deliver nanoparticles to tumor cells and then shine the right light on them, they will get hot and then they will burn the region around. Similar things that you can do with plasmons is that when you excite a plasmon, right, the plasmon absorbs a lot of energy. That energy is essentially contained in the movement of the electrons that give rise to the plasmon. But after some time, the electrons start to dephase, and then some of them can start to gain the energy that was before shared by all of them. And then those electrons get energies that are well above the thermal energy of the system, and then they become what we call hot carriers or hot electrons, and those can be transferred to molecules that may be around and induce some kind of photochemistry, or then, of course, they can also be used if you transfer them to circuits to do improve photovoltaic devices, or even to do photo detection. More recently, the community is also looking at using plasmons to produce colors. Definitely, you've seen an example, like the Licardius cup is a very beautiful example of how, by engineering the shape and the size of plasmonic nanoparticles, you can produce very vivid colors, which are, if you want, colors that come from they are structural colors. They don't come from a chemical origin. They are just due to the geometry, and therefore they are expected to be much more robust than pigments or dyes that typically tend to photo bleach with, as time goes, right? And then you can also use plasmons to produce light if you combine them, of course, with materials that can provide gain. And that is a path, for example, to create nanoscale light sources, including nanolasers. So all of those properties essentially, all of these applications share or utilize the ability of plasmons to confine light and produce very strong fields. Now, of course, when we think of using nanoparticles for doing any of these applications, we never use just one. We tend to put more than one and produce some kind of clusters. And one way that turns out to be very interesting of arranging nanoparticles to produce interesting devices is a periodic array. So place them in a order kind of a structure. So the idea, or the reason why we do that, is because this ordering can produce kind of new type of resonances, or can produce new type of collective effects. And the way you can understand that is the following. So imagine you have just a single particle, a single nanostructure, as the ones we've been looking at. If you look at the spectrum, and you can think of anything, the absorption cross-section, the extinction cross-section, the scattering cross-section, whatever you want, the optical response in general, is going to have a resonance, right, at the frequency at which this particle has its plasmon resonance, right? And then, of course, you can describe this in a very simple way using probably one of the simplest approximations, which is considering this particle, since it's very tiny, much smaller than the wavelength, you can consider it as a polarizable object, as a little dipole that you are exciting when you shine light. And therefore, you can describe the response through a induced dipole, which is proportional to the external field, and of course, is proportional to the properties of the particle that you describe through a polarizability. If you have two particles or more, like multiple particles, but still a finite number of particles, then you can kind of generalize this a little bit and say, okay, now the dipole that I induce in particle I is going to be the dipole produced by my external field, but also I have to sum the field produced by the rest of the particles, right? Because I am exciting all of them, and then they can produce a field at the particle I'm looking at. Okay, and of course now what is important is to characterize that interaction, right? And then you can do it through the dipole-dipole interaction tensor, whatever you want to call it. It's just the field that the dipole produces at the position of the other particle. And then you can, if you see, this is just a system of equations with 3 equations per particle, because you have 3 possible orientations of that dipole, and then you can always solve it. Of course, you need to invert a matrix, which is given by this factor here. Is just 1 minus alpha times the polarizability times, the polarizability times the interaction. But if you are able to invert this matrix, or in other words, to solve that system of equations, you can obtain the response of the system. And for instance, if you have 2 particles, then typically you're going to get 2 resonances, okay, because there are going to be different ways between the orientation of the 2 particles. Now, what happens if instead of that, we keep adding particles, and then Of course, what happened first, as you can imagine, is that at some point you will not be able to solve this system of equations because you will have too many equations. Okay, so at that point, one thing you can do is like, okay, I can just make an ordered array, so put them in a position such that they have some kind of periodicity, and therefore, instead of having to solve these 3n equations, now what I can do is just I can assume that because of the periodicity of my system, then my dipole has to also have kind of those periodic properties, no? And then essentially you just block waves, and then now your equation turns to be, instead of 3n equations, you come down to 3 equations only, okay? And then what you get, you see, is an equation that is very similar. You have the dipole, okay, the dipole wave, if you want, then is proportional or is equal to the sum of the external term, like the external field acting in all of them. And now you see your interaction now. You have to, if you want to Fourier transform, and then you characterize the whole property of your array just by only this kind of factor here, which people call lattice sum, but it's nothing more than just the Fourier transform of your dipole-dipole interaction tensor. And then you can also solve this. Now you, as I say, you are down to 3 equations only, and then you can solve that, and then of course you're going to obtain a certain resonance. Okay, you can think that you see what you end up having is going to be similar to what you had before, right? This is the, if you want the dipole induced just in a single particle, and then you have this factor that is modifying that. So you are getting typically a shift compared with the single particle, maybe something like that. But then this equation also tells you something interesting. So what if this factor actually becomes 0? Because so far, the resonances that we see here are associated to the resonances that the single particle has, no, because it has a certain polarizability and support plasmons. But then what if now we can cancel this? If we cancel this denominator, then we're going to have a new type of resonances that are not just due to the single particle. They come also from the interaction between all the particles that is kind of encoded in this factor here. But then how you can cancel this factor? Because usually we know that if you have few particles, usually the polarizability is always, when you multiply by the interaction, that's something that is always smaller than 1. It's kind of a perturbation, right? If you see, like when you have 2 particles compared with 1, what you get is that the modes are changed a little bit, right? But not that much, because this term typically is smaller than 1. So how we can make that bigger? Well, the answer is like we can work with a periodic array, but now we have to make the periodic array, the period of the array has to be comparable to the wavelength. And therefore, what we are going to be using are the diffraction orders of the array, no, in order to boost that interaction. So the idea is the following. So if you can write the equation for the induced dipole on the particles, you can rewrite that taking this alpha inside of this denominator. And now you see, whenever you are able to make your polarizability, the inverse of your polarizability, equal to this interaction, then you're going to have a mode. And you're going to have a mode that is not a plasmonic resonance anymore, right? Because it's not a pole, if you want, on the polarizability. It's actually the cancellation between the polarizability, the inverse of the polarizability, and the interaction. And then, of course, this interaction, this is, as I say, the Fourier transform, if you want, of the dipole-dipole interaction. And you can see that when I have 2 dipoles interacting, right, if they are very close, they are mostly interacting through the near field. They interact through a coupling that decays with the distance cube, right? If I go farther, then I have also a term that goes as 1 over the distance squared. And if I go far away, the only term that survives is the far field coupling, right, which goes as 1 over the distance, no, 1 over the separation. But if you think on the array, as I go farther and farther, if you look at the, imagine you pick up one particle, and then you start looking at how this particle interacts with particles that are farther and farther. Eventually, the interaction, as I say, is 1 over the distance. But as I keep increasing the distance, I am getting more particles, right, that interact. And the number of particles that I add to that sum grows with the area of my array, right? Therefore, the number of particles that I am adding grows as r squared. However, the interaction decays only as 1 over r. So it looks like if I am clever enough, and of course what clever enough means is that if I am able to make this factor, this oscillating factor, not to oscillate, then I will keep adding interaction to my system, and therefore I will have an infinite, if you want, resonance. And that's exactly what happened. If you plot this factor for, I'm plotting here for a square array at normal incidence, of course there are regions or there are wavelengths which coincide with the Rayleigh anomalies of the system, the diffraction orders became increasing, where this sum becomes infinite. Why? Because for that particular wavelength, you see, I'm hitting a factor in which essentially the distance between any two particles is going to be times the by the way vector, in which my case is just normal incidence, is not going to give me any phase. I'm going to be summing everything on phase, and therefore I'm going to have an infinite value. Okay, and then if I plot now the inverse of the polarizability of my particle, I'm going to get something that goes like that. So anytime that I cross, the red line with the blue line, I'm going to have a strong resonance. And this is the type of spectrum that I'm going to expect. So I'm going to have the typical plasmon supported by each of the particles, which will happen whenever you see the polarizability has a pole, right? When the polarizability crosses 0, 1 over the polarizability crosses 0, I'm going to have a resonance, but that's the resonance of each of the particles, maybe modified because of the interaction. But then I'm going to have other type of resonances here, right, whenever these two quantities cross. And this resonance is what we call lattice resonance. It's a resonance that is a combination of the collective interaction of the particles and then the fact that each particle itself can have some polarizability. And then these resonances, because of their geometrical origin, they tend to be very narrow and have very strong responses. Okay. Of course, these resonances appear at wavelengths at which that are essentially commensurate with the periodicity. So wavelengths for which the interaction between all the dipoles in my lattice becomes in phase. So then, if I look at that particular dipole, this dipole is going to be interacting with all the other dipoles in phase. So every dipole, even though the coupling decays with the distance, I'm putting more and more particles interacting with my original particle. And of course, that's going to happen at the wavelengths that are essentially defined by the lattice through the reciprocal lattice vector. The frequency, the wavelengths that satisfy this condition, which is, of course, the wavelengths at which you have the Rayleigh anomalies of your array. Then these lattice resonances have been used a lot in the past for doing a lot of interesting applications because they have an advantage compared with usual plasmons, that is that they are very narrow. One of the biggest problems with plasmons is that they tend to have a lot of losses, and therefore they tend to be, the resonances tend to be very broad, spectrally. However, these ones are very narrow, and of course that can be used to for example, for very narrow light sources or nanolasers. They can be also used for sensing. You have something extremely narrow, and that comes from the periodic kind of geometry of your system. So as soon as you put something near the system, some dielectric environment that is different from what you used to have, then that's going to affect the response. It's going to shift the response, and therefore you can use it for sensing. You can also use it for producing colors. If you want to produce a color, you want to have a very narrow resonance, right? You want to have a very pure color, right? That looks vivid and strong. And also, it has been used, for example, to look at bosons and condensates and other type of interesting physics. So what we did here, our first idea was, okay, this is clearly a field that have been there for many years and a lot of people working, but most of the research that we could find was focused on arrays that have a geometry, like for example, this one, a square array with one particle per unit cell. And our naive approach was like, okay, but what if I start adding particles to the unit cell? Of course, the obvious response to that is that I'm going to get a response that is much complicated than if I have a single one. But then is there any way that we can predict that response in a simple way, so we can just place the particles in the right positions to produce some optical responses that may be interesting? And what we did was to kind of take a different approach, because if you think on, for example, an array like this with 2 particles per unit cell, right? You can always think of this system as to be that, like I have an array and I have 2 particles in the unit cell. But you can also think of this system as 2 arrays equal with exact same periodicity that are placed both of them in the same plane, and then they are displaced, right? If you look at the blue or the red array, they are exactly the same arrays, exactly the same. I'm not talking about each of the particles, this comes later. If I only talk about the positions, it's the same array but displaced, okay? And then we know that if we have just two particles that we saw before, and then I place them together, I'm going to have two modes, right? Why? Because if each of them supports a dipole, then when I place them together, I'm going to have a mode in which the two dipoles are aligned, and I'm going to have another mode in which the two dipoles are not aligned, right? This is the so-called hybridization model, if you want to call it that way, or just the basic interaction. But now, if I think the same way with my two arrays, I say, okay, I have my red and blue array. If I put them together, I'm going to get something similar. I'm going to get some kind of mode in which the particles are aligned, all the dipoles are in the same direction, and another mode in which they are different. Well, something that is important is that when you think in localized particles, like just two, when they interact, when you put them close, they interact through the near field, as we were mentioning before. And therefore, this interaction is, if you want, a little bit boring, no? Because the only thing you can do is like make it bigger or smaller, right? You put them a little bit farther, the interaction decreases. You put them closer, the interaction becomes stronger. But that's all. However, if you think carefully, in this case, the interaction is between two modes that are completely delocalized, right? I have a mode in this lattice that is one of these lattice resonances in which I'm exciting all the dipoles. It's a collective mode. And then I have a similar collective mode in the other lattice. So when I put them together, they don't interact through the near field. They actually interact through the far field. And therefore, the far field is much more interesting in the sense that now you have this exponential. So your interaction can be positive, can be negative, or it can be zero. Okay? So now just by moving these particles, one with respect to the other, and of course you don't move just two particles, you move the two arrays, you can now tune the coupling in a wide range, because you can make it either positive, negative, or zero. So then what we did was to kind of generalize this dipole model that has been used by many, many authors in the past. But now the idea was to generalize it to deal with a system in which we have multiple particles per unit cell, not just one. Okay? That was very simple. The only thing you have to do is now, instead of having vectors with 3 components, you have vectors with 3 n components, where n is the number of particles in the unit cell. You get a little bit more of algebra, but you can do exactly the same as we did before. Go to the Fourier space, change everything as block waves, and now you end up having the same type of equation, right? Where you have this denominator, and when this denominator cancels, you are going to have your lattice resonance. But the difference now is that the lattice sum that you had before here, that was, of course, a 3 by 3 matrix before, no? Like you have x, y, and z components. Now, it's going to be a 3n by 3n matrix. In the diagonal, you're going to have the all lattice sum for a single array. But now, off diagonal, you're going to have the lattice sum between different particles in the unit cell. You're going to have the array of particle 1 with the array of particle 2, and so on and so forth. So everything you need to do is just to understand this coupling. If you understand that coupling, you can predict the response of your system. So for example, if you have a system with 2 particles per unit cell, then you get in principle, you will get a 3 by 3 matrix, 6 by 6 matrix. But if you assume normal incidence, then you cannot excite any C component. It becomes 2 by 2, and due to symmetry, there are some couplings that are forbidden. If in addition, you keep simplifying this and you go to the first Rayleigh anomaly, so you work close to the wavelength being equal to the period, then you can prove that there cannot be XY coupling because of the square geometry. And therefore, this matrix becomes much smaller. Actually, it can be reduced to essentially a 2 by 2 matrix, like this, where you see I have taken the lattice sum of the single lattice outside, and then I have here just the coupling, the relative coupling between the 2 arrays. So then that's everything you need to know in order to describe your system. And of course, that tells you how the red and the blue array interact. And then if you come back to your problem, so the dipole was just equal to the dipole induced by the external field plus the dipole coming from the rest of the particles, then you can recast this as an eigenvalue problem where you just have, you see the interaction matrix times the polarizability. When this is equal to this, then you have a mode, right? So then all you have to do actually is to calculate these 2 factors and then diagonalize this matrix, and then you get the modes. And now, what is interesting is that you can calculate these factors as a function of the position of particle 2 with respect to particle 1. And this is what you get if you look at the x component or the y component, which of course are the same but just rotated. So essentially, you see what we were predicting. These factors, which determine the coupling between the two arrays, can go all the way from being negative to being positive or zero, no? In the scale of the single lattice resonance. As you see, you can put it, the second particle, you can put it here, and then you get 1, you can move it around, and you get different values. So, for example, imagine that we place our second particle exactly at this position here. So then we have an array like this. And then, you see, there we have a coupling that is exactly 0. So in other words, we have just the identity matrix. And therefore, if I diagonalize the identity matrix, it's already diagonal. So I just have 2 modes, right? Now is where, and of course, one mode comes when the real part of this is equal to the real part of that, and the other mode comes when the real part of this is equal to the real part of the second particle. If now I choose 2 different particles for my 2 arrays, for example, we choose 2 cells, nanocells, with silver and silica. We use that because for us it's much easier to model spherical particles, but then of course you could choose anything here. You see they are slightly different. This is a little bit smaller than that one. Then, you know, when we place them, based on this, we expect to see 2 peaks in our spectrum, right? And we expect to see 2 peaks in which, in one of them, only one particle is excited. In the other peak, only the other particle is excited. So if now we do the full calculation, we just get that. We get 2 resonances instead of 1 lattice resonance. Now we have 2. And indeed, if we calculate the induced dipole, we are plotting here the imaginary part of the induced dipole, you see that in one of them, you only excite the particle, the red particle, the particle 1, while in the other one, you only excite the other particle. So now we have an array with 2 particles per unit cell that gives you 2 resonances, in which in one resonance you only excite one particle, and in the other resonance you only excite the other. Of course, you can think of this, what we are doing, in other words, is to put the second array exactly at the nodes of the field produced by the first array, so they don't interact. But then we can do a little bit more complicated. We can move it here, and then we have a negative interaction, as you see. So we have this matrix. If we diagonalize that matrix, we get only one physical mode, because the other mode will require a 0 polarizability, and therefore will not have any resonance. But then you see this mode comes with this at this position when these 2 things are equal, and it has this kind of mode, no, where one particle is excited with minus the polarizability, the other one is excited with the plus. If we calculate what we get for the reflectance, we see 1 peak as expected, and then if we look at the induced dipole, we see that we are essentially exciting the 2 particles in different directions. So one dipole is opposed to the other dipole. Now, you can also understand this from the point of view that we are putting now the second array in the antinodes of the first one, and therefore is seeing kind of a field that opposes to that. But of course, you can do more complicated things. You can go and, for example, work in the second radiate anomaly, where now you are going to have coupling between x and y directions. And then, you know, for instance, if you choose the second particle to be essentially in this position, now you can just go to those diagrams, populate all the terms in the matrix. You get a matrix like this. You diagonalize. You get 2 modes. Now, of course, we have x and y for particle 1 and x and y for particle 2. And these are the 2 modes that you get that actually are degenerate. They appear at the same wavelength. And now imagine that I come with my electric field, normal incidence, but now I play with the polarization. I rotate the polarization of my incident field, and then I choose an angle theta with the x-axis. Now what happens, so this is essentially the field that I'm using to excite the system, you know, written in the same kind of basis as this. And if you see, when you multiply this vector by this or this vector by that, you realize that you are exciting the 2 modes that are degenerate with exactly the same amplitude, which is given by the sum of the cosine and the sine. So that tells you that essentially you are exciting the 2 modes exactly with the same amplitude regardless of the angle. So you have a system for which you are going to excite a dipole that is going to be locked. And it's going to be independent of your polarization. So let me show you. You have here the resonance. Of course, if you come with x polarization or y polarization, you get the same resonance. But now if you look at the induced dipole, this is the x component of the induced dipole as a function of your polarization. But now if you look at the y, it's exactly the same. That means that regardless of your incident polarization, the dipole is always oscillating at 45 degrees. Always. It's locked. You can change your incident polarization and it never changes. And you are locking it through the coherent coupling between the particles. Of course, this is very different from the usual configuration in which if you rotate your dipole, sorry, your polarization, then your dipole rotates accordingly. It's following your incident polarization. You can do other interesting things, like for instance, you can have a more complicated array like this one, which has just a mode like that, in which you are exciting two particles in one direction, the other one in the other direction. And now you can come and say, okay, can I put a fourth particle in my unit cell such that it doesn't interact with any of the other three? Well, if you look at the interaction kind of diagrams, you see that there are 4 points for which both the XX and YY and also the XY components are 0. So then if now we place a particle in one of these spots, you see that now the reflectance that we get is exactly the same. You see you have the same peak there, but now we get an extra peak. And if we look at the induced dipole, we see that essentially at this peak we have exactly the same as we had before, but now we are getting another peak in which we only excite that yellow particle. Even though, this yellow particle is quite close to the blue one, still it's like they don't see each other because of these collective interactions. Okay, so everything I've been talking so far has been focused on the far field properties, right? I come with my plane wave, and then I look at the reflectance, the transmittance, and I try to place my particles in a way that they give me a nice or an optical response that I want. But what about the near field, right? What happens if I go close to the particles? Well, we know that, again, let's go now for simplicity to a simple square array with one particle per unit cell, like this one. We are going to come with some light here, incident of my system. I know, of course, if I look at if you want the dispersion diagram, and then I look at these radiate anomalies, I know my lattice resonances appear always very close to the radiate anomalies, because at the radiate anomalies is where my interaction becomes infinite, and then I want to work close to them in order to cancel the inverse of my polarizability. So you see, you have, as a function of the angle, you have many different anomalies. And if you look at, for example, close to the first order radiate anomaly, and then you look at the reflectance, we have these lattice resonances that we've been discussing, and then they can get very narrow, and they can give you a very strong reflectance. So for example, in this case, with a particle of a diameter of 160, with a period of 800, so it's mostly vacuum, you just have little particles separated by like almost, let's say 8 times or 6 times the diameter, still give you a reflectance that is almost equal to 1. And this is because we are canceling this denominator, getting a strong lattice resonance. But then because of the same reasons, we should expect that since we are getting a very strong dipole, we should get a very strong near field. And then what you can do is to write the expression for the near field using the couple dipole model, which is terrible. But there are a few things that are interesting. The field that your system produces is a sum, of course, over reciprocal lattice vector. It's a sum over diffraction orders. That's not surprising. But then, and of course, it's proportional to the induced dipole, which is this quantity that we say can be very large, right? But it has this other term here, which is quite interesting. If you think it's an exponential, right, which controls whether your diffraction order is going to give you a radiative mode, so something that propagates away, or an evanescent mode. But then also has this square root in the denominator, which will control how strong your mode is, right? And before, what we have been looking at is like if we send a plane wave, we have been looking always at the 0 order, which appears for a reciprocal lattice vector that is 0, and therefore this exponential here with this factor is just a plane wave that propagates along the z-axis, right? And then it has just a factor proportional to 1 over the wavelength. Now, if you go to the next order, okay, of course now the reciprocal lattice vector is something like this, and now what you get in your exponential, right, is something that is essentially 2 pi over lambda square minus 2 pi over the period square, right? And then there is something interesting here, because I told you that we are always working on the red side of a radiate anomaly. And if we work on the red side of the first radiate anomaly, essentially on the red side of the wavelength being equal to the period, what happened is that then these two diffraction orders actually have this factor here is larger than that. No, I'm telling you that lambda is a little bit larger than a. So this square root is just a complex number, right? It's an imaginary number. So then what I have exactly is an evanescent field. It's not a propagating wave. And you could say, well, and what? Well, look at what happened if actually now I try to move for whatever, I mean, I don't know how, but imagine if I could move this resonance closer to that point. I will be making this factor closer to that factor. So even though it's still an evanescent mode, it will be extending farther and farther from my array, right? But at the same time, look at this. I will be canceling this denominator. So in addition to having a very strong dipole, because of having a lattice resonance, I will have this factor here, this essentially becoming 0 and diverging, okay? Actually, you can just work out this a little bit, make some approximations, and write the field at a certain distance above your array, the average field at a certain distance on a plane, is given by this expression. You have all the properties of the particles are condensate on this factor, where you have the cross-section, the absorption and the scattering cross-sections of each of the particles, and then you have this exponential and then this factor. And we have defined delta to be the distance between the wavelength at which we have the lattice resonance and the period, right, which is that. And you see that if we can make this delta factor 0, we'll get a field that essentially becomes as large as we want, and at the same time, it's going to decay as slowly as we want. Okay, now the question is how we move the resonance closer to the right anomaly. Well, we know that the resonance comes whenever this factor becomes 0, when the polarizability, the inverse of the polarizability, is equal to the lattice sum. We know that the lattice sum, as we approach to that Rayleigh anomaly, the lattice sum essentially goes to infinite. So then, if we make the particles smaller and smaller, the polarizability becomes smaller, and the inverse of the polarizability becomes larger. So for example, for a particle with a diameter of 160, you have this inverse polarizability, and if you keep making it smaller, it goes up, and then you see we are shifting the position of the peak from here to here to here. You see we are making it closer and closer to the Rayleigh anomaly. And if our model is correct, we should expect to see a field that is larger and larger and larger. So if now you go and do a full calculation, solving Maxwell equations numerically, this is what you get. This is the resonance you get for a diameter of 160, calculated at a distance equal to a period away from the resonance, from the array. If I make it smaller and smaller and smaller, you see my field becomes larger and larger and larger. And look at this is the field average on a plane. It's not a, we in plasmonics we are used to see very strong fields close to the particles, as I showed you at the beginning. This field is calculated one period away. It's essentially one wavelength away of the array, and it's average over the plane. Okay, it's not a hot spot, and still you can make it like 10 to the 5. And at the same time, this predicts that if we calculate it farther away, it shouldn't decay. And you see that when we go for the largest particle, you see when you go to 2 periods or 3 periods away, you see the field goes down. However, when we go to a small particle, the 3 lines remain one on top of the other. So the field doesn't decay. Of course, you can do the same. Instead of making the particles smaller, you can also play the same trick by making the period larger and keeping the size of the particles fixed. And this is what we have here. Diameter is fixed. We just change the period, and we have the same behavior. Let me show you here in a different way. So this is the same plot as we had before. And what we have here is for each of these cases at the resonance, I'm plotting the field as a function of the distance above or below the array. And you can see that for this one, of course, it decays. For this one, it decays, but slowly. And for the 40 nanometers, almost become flat. And the same happens with the other case. And now what I'm plotting here is just these dashed lines is this simple equation plotted on top of the color lines, which are the full numerical results. So you see that actually this simple model predicts the near field very well. And of course, by this point, probably you are thinking like, okay, you're telling me that I get an array, I have some field enhancement, and then I make the particles smaller, and you get more field. I keep making them smaller, and I get more and more field. So then why not I go just to 1 atom or half atom if I could, no? So essentially, what is the catch, no? What is the catch of all of this? Well, there is a trick that we typically forget, which is the fact that our array in reality cannot be infinite, right? Everything I'm showing here is for a periodic array, and a periodic array by definition is infinite, okay? So what if instead of having an infinite array, I actually have an array that has some finite size, so let's say m plus 1 particles by m plus 1 particles. Of course, I could try to solve this using the couple-dipole model, but if I want to go to many particles, then I will not be able, because I have to invert a huge matrix or solve a huge system of equations. But then what I can do is kind of revisit what I was telling you. You see, the trick we were playing to move the resonance closer to the right anomaly is just to make the particles smaller. And that was working because my lattice sum was essentially as big as I want, right? Why? Because I was calculating it for an infinite system. So then, an infinite system, I can keep, like the interaction of my particle, I have an infinite number of particles. So even though they are contributing weaker and weaker, like the interaction is weaker and weaker, as I go farther, I am adding more particles, or particles at a faster pace than my field is decaying. But if I have a finite array, what happened with the lattice sum? So what I'm going to show you now is what happened with the lattice sum if I only have, let's say, 500 by 500 particles. You see, my lattice sum can only reach here, and then I cannot go beyond that. Of course, if I keep increasing the particles, I go bigger. But in order to reach these crazy limits I was telling you, we are predicting a very large number of particles. Of course, now is where the fabrication comes. If you are able to make an array that is large enough so you have enough particles interacting, of course you can make your field as large as you want, because at the end you are summing the field that is contributed by each of those little particles that you have. But then you are going to be limited by how many particles you can make your array, and how many of them are actually interacting coherently. If you have defects, if your particles are not all equal, or the distances are not equal, of course, effectively you are going to be decreasing the number of particles that help you. But then this is telling you what is the limit. So the limit is essentially how many particles you can put in an ordered array. The more you can add, the stronger the field that you can reach. Of course, you can elaborate, or if you want, you can discuss potential applications. For instance, now you can put a dielectric slab at a certain distance with an index that is literally like vacuum plus a little thing. And you can see that as you make your particles smaller, so this is the biggest case, you see when you put this at a distance of 1 period or 4 period, and then your, let's say your index is just 10 to the minus 3 or 10 to the minus 4, you can see a change in the reflectance. And of course that change in the reflectance becomes bigger and bigger as you make the particles smaller, because you have a stronger field, as we were discussing. But also that makes your system more sensitive to the environment. So essentially, the larger your array can be made perfect, let's say, the more sensitive you are going to be to the environment. And as you say, it is crucial to understand what happens when you have finite arrays. If you just rely on these models, assuming periodic boundary conditions, infinite systems, you can essentially predict an infinite field enhancement. I mean, it's never infinite, but it approaches to infinite as you make your particles smaller and smaller. So then we decided to analyze also what happens if you have systems that are not infinite, they are finite. And then we were looking at two different limits. The limit in which we call long-range coupling, which is what I've been showing all the time, so periods that are comparable to the wavelength, but also the limit that is used, for example, when you work in meta-surfaces or metamaterials, in which now the particles are way closer than the wavelength, and then they can produce, if you want, an effective response. No? And what you realize is that, for example, if you have an array of gold nanoparticles separated by just 5 radius, so a separation much smaller than the wavelength, you see that for one particle you get that. For an infinite number of particles you get something like that. So actually with 4 by 4 particles, 2 by 2 particles, a number of 4, then you almost get there. If you keep increasing, now 400 particles, of course, is almost indistinguishable from infinite. Now, if I make the array, I put the particles closer, the interaction is stronger, and therefore you need more particles to reach the infinite, the perfectly periodic limit. Okay, you see that here you almost have to go actually to 400, while here with 4 was almost enough. If we substitute gold by silver, which gives you typically more like a stronger response, narrower resonances, you see that now it's necessary like almost 400 for 5 radius separation, and also for 3 you have this big change between just having 1 or having an infinite array. Now, we have done that also for other materials, like for example, graphene. Graphene arrays have been used for example, for photodetection or for achieving some kind of extinction or some kind of optical response that is tunable, because you can just change the Fermi level. So graphene is essentially, if you want, a tunable metal. It's a material that if you add electrons behaves as a metal, but then depending on how many electrons you add, you can change the plasmon. And the coupling strength between the different nanodisks will be proportional to the level of doping, so the Fermi level that you achieve. And then you can see that if you have just one or an infinite array for a small doping, small interaction, it's almost the same. So you just need like maybe 25 or 100 disks to get almost the infinite limit. If you go to stronger couplings, so stronger Fermi levels, you see now you actually have to go down to up to almost 900 nanodisks to actually recover the infinite limit. Okay, so you essentially have to get more. So the message is like the stronger the coupling is, the more particles you need. But there is something, I don't know if you have realized, there is something interesting on how you approach this infinite limit. In particular, when you look at the graphene cases, you see we are approaching to the infinite limit. So here is essentially the shift with respect to the infinite limit. So the line will be the frequency of the infinite limit, and this is for essentially for 1, for 10, so on and so forth. And you see we approach from the blue side, so the frequency is decreasing. Okay. However, if we go to higher Fermi levels, we have some kind of a strange oscillation around. And indeed, if we plot the cases for silver and gold, in this case, you see you come from the left side. So it looks like I give you an array, you start making it bigger and bigger. Of course, you tend to the infinite limit, but depending on some properties of the array, you come from the blue or the red side of the resonance. So we were kind of, we were not expecting this. We were very confused. What is telling you that you should come from one side or the other side? And actually, we realized that indeed what controls that is that if you realize, again, we have this kind of denominator, and then the sign of the coupling is what determines whether you are gonna, as you increase the number of particles, you are gonna come from, you're gonna reduce your frequency or you are gonna increase your frequency. And indeed, you can do a very simple thing. If you just write the dipole-dipole coupling just for the first neighbor. So I have a particle and I just look at the first neighbor. You have something like this. And now, depending whether retardation is negligible, if it is, then the real part of this just becomes something like that, which is positive. But if retardation is not something you can neglect, then of course now we pick up the cosine. It's the same idea as before. We have an exponential, and now depending on the actual value of that cosine, the coupling could be positive or negative. And that's exactly what we saw. For silver, for example, you see this is the result for one particle as a function of the radius, and then now we have here the result for the array. You see, for a periodicity of 3 times the radius, or for a periodicity of 5 times the radius. You see, as we increase the size, we are increasing the retardation effects, and you see how at some point, you see our resonance starts to be on the red side and suddenly change to the blue side. The same happens, if you keep adding, increasing that. So this is what I was telling. So this is the infinite array. This is a single particle. This is a single particle for another size, and this is the infinite array. So depending on the size, and therefore depending on whether the retardation is important or not, you come from one side or from the other. And the same applies, of course, for this is gold. Exactly the same. In gold, everything is weaker, so the shifts are much tinier, so it's more difficult to resolve them. Now, something that is important is I have shown you the convergence of the far field properties. What I was always looking at there was the extinction cross-section of my array. Of course, when I have an infinite array, I have an extinction per unit cell. When I have a finite array, I can calculate the extinction of the whole array and divide it by the area, right? Now, what happened with the near field when I do that? Well, we have seen that for example, for silver particles, when they were like 5 radius away, we've seen that with maybe like 100 particles or so, the extinction was almost indistinguishable from the infinite case. However, if we look at the near field, what we look at here is actually not the near field itself. We look at the induced dipole, so the local, we call it the local extinction, so the imaginary part of the dipole at each particle. And then what we do is calculate the difference between that value and the value that we'll get for an infinite array. In an infinite array, every single particle is exacted equally. We are coming with plane wave, normal incidence, so all the particles have the same induced dipole, right? However, you see here, for 25 particles, even though the extinction was almost perfect, you see you don't have the same induced dipole in all of them. And you can see here that at the center, you get a result that is very similar to the infinite case. It's almost indistinguishable. But when you go to the edge, you have big difference. And you can claim that, of course, that's what you expect. No? Like, if I am truncating my array, I will expect that affects more to the edges than to the center. But then what is interesting is that you see in some cases, that could be actually giving you changes on the local extinction of each particle that can be 50%. So even though you could have predicted, okay, this 25 or this 400 particle array give me the exact same extinction as an infinite array. Well, wait, if you are going to work with one part of your array, you better work at the center, because on the edges it's going to give you something. Now, if you go to graphene, which gives you a stronger interaction, now, of course, the variation you see can be quite large. You can be having like 100% difference with what you will be predicting with the infinite array model. Now, what I showed you is for this short range coupling, particles are closer than the wavelength, but what if we go to the limit in which we have lattice resonances? Well, now everything is quite complicated, much more complicated, because those lattice resonances are a collective effect, and therefore they are going to be much more sensitive to the fact that you don't have an infinite array. So here is what we get for when we separate the particles 400 nanometers. This is for one particle, and this is for the infinite array. This is a nice lattice resonance. Now I'm plotting in energies. Before I was always showing everything in wavelengths, but this is the exact same thing. And of course, now we need to really put many particles if we want to really resolve these sharp features. You see, we went up to 10,000 and still you can claim that it was not. And this is, of course, not the narrowest resonance you can get. You can get way more narrow resonances if you play some tricks. And you see, when you calculate the induced dipoles, you see that, of course, you have very strong edge effects. But in the center, because it's a very collective effect, is kind of well matched to the infinite case. So this is almost everything I wanted to show you. We have been discussing this kind of idea of using more than one particle per unit cell and having a very simple model that allows us to predict the optical response. We've been looking also at the limits of the near field, and we have seen that if you can fabricate an infinite array, you can have a very strong field. If you cannot fabricate an infinite array, then the field will be not so strong, but still you can play your tricks to make it very large. And then we have been looking also at other types of finite size effects on arrays. And of course, the fact that arrays are finite change the optical response, and you have to consider that. And if I have like 3 minutes, I would like also to show you a very recent result, which has nothing to do with this, but I think it's very funny, is the fact that, you see, I showed you that plasmons were used by Romans, and that was this example of the Licardus cap. Well, we found another example, which are daguerreotypes. I don't know if you have ever seen any of these. So daguerreotypes actually were the first form of photography. It was the first technique that allowed human being to capture an image permanently. Of course, you can claim that the camera oscura was invented way earlier, but then was used to project images on walls, and then someone could paint it. But this was literally the first technology that allowed to capture an image on a mirror. And actually, it was invented by Daguerre in 19th century. It was disclosed actually in 1839. It was used for around 30 years, like crazy, because there was no other technology. And look at, there were 3 million of daguerreotypes made every year. Of course, nothing compared with selfies nowadays, but that was, I found really amazing. And then it was very widespread until it was substituted by better techniques. But then what is very interesting is that the reason why a daguerreotype works is just plasmonics. So the reason why you see this image here is because when you fabricate the daguerreotype, what you are doing essentially is you are letting light fabricate little nanoparticles of silver. This is a silver film that is sensitized to light, and then when you expose it to light, then that silver film becomes like nanoparticles with the right size to scatter light in the visible and therefore produce your image. Now, a problem they have is that daguerreotypes are degrading faster than we would like. And you can imagine that these are the only images we have from these 30 years since they were invented to the moment where we had a better technology, and therefore it's very important to preserve them. This is a daguerreotype was made on 1850, and it was a picture of the daguerreotype taken in 1930s. And you see, they repeated the picture 40 years after, and you can see how it's being degraded a lot. In particular, you have all this white haze and a lot of spots. And it's amazing that only in 40 years, you have gone from almost something, I would say, pretty nice to something that is quite degraded, while since 1850 to essentially 1930, it was almost not degraded. So the question is, what is affecting that? And that's actually a very important problem for some collaborators of us that work at the Metropolitan Museum in New York. They have a very amazing collection of daguerreotypes, and they are very interested in understanding how a daguerreotype works, what is the optics of the daguerreotype, because they are finding that the daguerreotypes are degrading faster than they would like. So we collaborate with them because we can do some theory in plasmonics, basic things. And then, as I was telling you, the image on a daguerreotype is produced by scattering by silver particles. And this is actually a TM or a SEM image of this daguerreotype. And you see at this point, you have a lot of nanoparticles, all these white points, with a size of the order of hundreds of nanometers, which is exactly what you need to scatter light in the visible. If you go to a region, like for example here, that is much darker, you have particles, but these particles are way too big to scatter in the visible. They actually scatter in the infrared, and you don't have so many. And indeed, if you go to other, even darker regions, you have nothing. It's just, you see nothing there. And there are other regions here where you have, again, I don't know if you can see, there's some kind of little color there. So what we did was to get some SEM images from our collaborators and do a very simplified modeling of that. So, okay, we have just a silver bump on the surface, and then we illuminate with light, different polarizations, and of course we study different sizes, different geometries, and of course, as you can imagine, the surface is a mess. There are not two particles equal. It's a huge variety. And then the first answer we gave them is like, okay, we cannot do anything. I mean, we can essentially, we are going to have a different response if we change the size or this, you know, it was very difficult to get some general trend. But at some point, after many calculations, we realized that, you know, all these particles, regardless of the size and even regardless a little bit of the morphology, they were all producing two resonances. This is the scattering spectrum. So you will always have a resonance in the red part of the spectrum and a resonance on the blue part of the spectrum. And you see the resonance on the red part is excited both by p-polarized light, okay, light that comes like that, and you know, both of them are excited, but the blue resonance is only excited by s-polarized light. So we were doing a little bit more modeling, and we realized that actually the blue resonance is a dipole that is horizontal. So you come with light, and then you see the dipole oscillating parallel to the film. While the other one, it was a vertical dipole, which was possible because, of course, you have metal on a metal, so the charge can flow from the particle to the metal film and back. And then the nice thing is that this dipole, since it's transversal, is going to emit light perpendicular, like normal to the surface. While this other dipole, since it's kind of vertical, is going to emit like a donut. Okay? So we were like, okay, well, the only thing that we can tell you, actually, is that if you look at a daguerreotype, based on these calculations, you will predict that if you look at normal incidence, you look at kind of normally, you should see some kind of bluish tone, right? Because this peak is always on the blue. So you should see some kind of blue hue around the daguerreotype. While if you look at high angles, it should look more red. But we didn't know anything about daguerreotypes, and we thought that they were just white and black. So we're like, I don't know, we are predicting some color. But it turns out that that was actually something that they knew for many years, and no one had actually explained it. If these are a sample daguerreotype, because of course the Met didn't like us to, or them to break daguerreotypes to study them. So what they did was we contact this guy who is one of the few people in the world that actually can make daguerreotypes following exactly the same steps or the same recipe as in 19th century. And he was making tons of samples that we can play with. And then you can see that if you look at the small view angle, that means like almost normal, it looks blue. But as you rotate, you see it turns like kind of reddish or more darker. And actually, we have here a video of that daguerreotype. And you can see how as you go to normal incidence, the color change. It's not just white. It goes from some kind of red to some kind of blue. So that was very exciting because we were, even though there was such variety of particles, we could get some kind of general trends. And now what we are working with them is essentially to try to predict which type of chemical effects affect the image. So they are able to essentially get one of these daguerreotypes and then do all sorts of bad things, like expose it to high oxygen, different lights and everything, and then they can analyze how the morphology of the surface changes based on what they do to the daguerreotype. And then with that information, we can model the optical response that you will get. And hopefully, the idea is that soon we could tell them or try to find out which type of things are the ones that are producing the degradation. And we think probably it's going to be light, the UV part of the lights that are used in the museum. So that's all. Thank you very much, and sorry for taking a little bit longer.